Hello everyone, welcome to your physics teacher, and in today's lesson we're going to be looking at section 1.3 from the Nelson textbook, which looks at calculating the average acceleration when you're given a velocity versus time graph, and using the formula for average acceleration to find other things like the time change or velocity change in different type of questions. We're also going to be looking at how to calculate the instantaneous velocity, and that requires using a tangent. So we're going to start things off with question number 4. And question number 4 says, determine the average acceleration described by each of the following graphs. So there's a multiple part question. Now, the question is asking for the average acceleration. So just as a quick recap, the average acceleration is given by the change in the object's velocity over the change in time. Now, if we're looking at the graph, this is equal to the slope of the VT graph. So notice that in question 8, we're given a VT graph, so all we have to do is just calculate the slope of the given graph. Now, one strategy that we should use is to try to pick nice points. So what I mean by nice points is you want to pick points that line up nicely on the grid. So not the ones that are off to the intersection of the grid lines, but right at the grid line. So let me show you on the screen what I mean by that. So here, notice that we have one point that's really nice at the 5-second mark. So at the 5-second mark, the velocity there is 20 meters per second. And another nice point is actually right at the origin. So it's 0, 0. And to help us out in our slope formula, we could label this as x2, y2. And this is x1, y1. So this helps with the rise over the run formula, which is the change in y values over the change in x. So let's calculate this. You can think of it like y2 minus y1 over x2 minus x1, which if we put in the values, 20 minus 0, 5 minus 0, which is 20 over 5, which is equal to 4 meters per second, which is the same thing as 4 meters per second square. Right, as the units for acceleration. So that you should have learned already from a previous lesson. So this kind of makes sense. So in each second of time that goes by, the velocity gets faster by 4 meters per second. So we could double check this. From 1 second to 2 seconds, notice that this is approximately a rise of 4 meters per second in 1 second of time that goes by. So our answer makes sense. And again, recall for part B, they were just asking us to find the average acceleration of each of the graphs. So one strategy that we did is to find the slope of the VT graph. And in order to find the slope of the VT graph, we want to pick nice points which line up with our grid. So just look at the graph and try to identify the nice points. Yeah, one is right at the intercept, and the other one is at the 3-second mark. Again, you could have chosen any other points, but you are going to be approximating, so it is better to get more precise as you can. So pick the points that are nicely on the grid line. Let's label these as 0 and 5. 3 and 15, and to help us out with the formula is x2, y2, x1, y1. So again, write down your slope formula. You don't have to do this, but it's kind of like a way to remind yourself that you're calculating the slope. So now you just put in the values, 15 minus 5, 3 minus 0, so 10 over 3. So in this case, the acceleration is going to be 10 over 3 meters per second square. You can't really reduce that, and just leave it as a fraction. That's actually better, because this tells you that whenever 3 seconds go by, the velocity increases by 10 meters per second. So let me show you what I mean. So when 3 seconds go by, wait, let me erase these. When 3 seconds go by, your velocity should increase by 10. So from 5, it should go up to 15. So that makes sense. So you see, that's one way you can quickly check. Or maybe not so quickly, but at least you can check, right? And now that you gain the hang of this, let's do part C. Determine the average acceleration described by each of the following graphs. So we still have to do the same thing. The acceleration from a VT graph is just the slope. And in order to do this, let's find two nice points along the grid line. Oh, right away, the origin is really nice. And at the 5 second mark. So let's put in our values, which is 1.5 minus 0, 5 minus 0. So 1.5 over 5 meters per second. Okay, so this is going to be... All right, so now let's consider question number 6. So for question number 6, it asks, describe the motion of the object in all 3 segments of the graph shown in this figure. So we want to describe the motion. So we can break this down into 3 segments, it asks. So the first segment, let's call it A, B, C. So let's do question A, segment A. Or actually, you know what? That might get confusing, right? So let's call it the Roman numerals. I, double I, and triple I. So since we are looking at the velocity time graph, we have to remember that whenever we move away from the origin, we can say that it is speeding up. When it stays flat, in other words, the velocity here stays at the 6, the velocity is constant. And if the velocity goes towards the origin, it is slowing down, right? Because if you look at it from 0 to 1 second, the velocity went from 0 to 1.5, so it speeds up. But if you look at the 9 second mark to the 10 second mark, the velocity went from 2 to 0, so it is slowing down. So up to you how you want to remember it. The way I think about it is if it moves away from the origin, speeds up, stays flat, uniform motion. If it goes towards the origin, slows down. But when I say the word moves, I'm not talking about the object. I'm just saying the graph itself, so the trend line or the trend curve. So let's write it down. But we're not quite finished yet, because in order to describe the motion of the object, you need to specify the type of motion and also the direction of motion. But there's a convention that we follow. The velocity indicates the direction of motion. So when the velocity value is positive, it moves in the positive direction. When it's negative, it moves in the negative direction. So when we look at our graph here, notice that the values are always positive. So the whole time we have the object moving in the positive direction. But in this case, the positive direction is indicated by west, which is really confusing because normally you think of east as positive, but this graph is making it confusing. So the positive direction, in this case, they're indicating it to be west. So that's true for all of the three parts of the graph. For part B, it asks us to calculate the average acceleration of the object in all three segments of the graph. So the average acceleration, as we saw before, is just the change in velocity or the change in time. And because we are given the VT graph, that's just the slope of the VT graph. So let's calculate the slope in each of the three sections. So for the first part, between 0 and 4 seconds, it's probably best to pick out the endpoint because there's already nice points, right? They made the grid lines. So let's call this acceleration along the first part. So final velocity, which is 6, minus initial velocity was 0, and that took place in 4 seconds. So that's just 6 over 4 meters per second square, which can be reduced to 3 over 2. So that's kind of easy. For the second part, notice that the velocity value does not change. So we can have the acceleration for the second part. Final velocity is 6. Initial for that section is also 6. The time interval is between 7 and 4. But because the top part is already 6 minus 6, which is 0, and 0 divided by anything is always going to be 0, which we expect, right? Because if it's uniform motion, then it's not accelerating, so it is 0. And then for the third part, the final velocity is 0, and the initial one is 6. And this took place during 10 seconds minus 7 seconds. So minus 6 over 3, which is negative 2 meters per second square. Okay, so again, calculating the average acceleration, just calculate the slopes. Now I did skip a few steps, that way you could just read off the points and do it yourself, because I don't want to take up too much of your time. Let's look at C. Let me make this smaller so that way we have more space to work with. Okay, for part C, it asks us to calculate the total displacement of the object from 0 to 4 seconds, from 4 to 7, and from 7 to 10. Now we come across something different. So the displacement of the object, which is delta D, this is actually the area under VT graph. So this means that we're going to have to calculate the area in each of the three sections. So let's try to get color coordinated, so that way it's going to be easier for us. So we have the green section, which is between 7 and 10 seconds. The pink section between 0 and 4. And let's make it brown, between 4 and 7. So we have to calculate the area in each of the three sections, which is just going to give us the displacement. So let's do these calculations. And once again, we're going to do it for part I, double I, and triple I. So the displacement in the first part is just the area under the curve, because we have a triangle for the pink section. It's just base times height divided by 2. The base is 4 seconds, the height is 6. So 4 over 2 is 2, 2 times 6, 12 meters. You could check for yourself. The second displacement, oh, I should put the direction, sorry, west. The second displacement, we have a rectangular piece, which is just going to be the length times the width. So the length in this case is from 4 to 7, which is 3 seconds. And the width is this part here, so it's from 0 to 6, so 6, 12, 18 meters west. And the third displacement, we have another triangle, so base times the height divided by 2. Let's look at this. So the base is from 7 to 10, which is 3 seconds, and the height from 0 to 6. Divided by 2. So 6 over 2 is 3, 3 times 3 is 9, so 9 meters west. So the object was still moving west because it was a positive value. So that's how you calculate the graph here in this case. Now, that was the hardest part of the section. Now this should go by a lot faster, so I hope that it won't take up too much time. But if you're still with me, please hit a like and make sure you subscribe, that way you stay tuned. And for question 7, we have, what is the average acceleration of a sport car that increases its velocity from 2 meters to 4.5 meters per second in 1.9 seconds? Now, just write down a formula for the average acceleration, which is the change in velocity over the change in time, which we can write as final velocity minus initial velocity over the change in time. So now we just need to read the question more carefully. So we have a car that increases its velocity from 2 meters per second to 4.5 meters per second. So from, this is the initial, to will be the final. And it took place during a time interval of 1.9 seconds. So let's plug this into our formula that we have. Let me bring it a little bit lower. Okay, so the final velocity is 4.5 meters per second west minus the initial velocity, which is 2.0 meters per second west, divided by 1.9 seconds. So let's put this into the calculator. Now the reason why we're able to just add this up so nicely is because both of them are already west, so we can collect like terms already. So just punch it into the calculator. But if it was east and west, it gets more complicated. So I showed you that before already. Now we get approximately 1.31 meters per second square west. For question number 8, we have, if a child on a bicycle can accelerate at an average rate of 0.53 meters per second square, how long will it take to increase the bicycle's velocity from 0.68 meters per second to 0.89 meters per second? That's a mouthful. Very simply, they're asking us, they're giving us acceleration, they're giving us the velocities, they're looking for the time change. So the main formula from this section should be a giveaway. The acceleration is the change in velocity over the change in time, which is final velocity minus initial velocity. Right, then all we have to do is identify the different quantities in this case. So they give us that the acceleration is 0.53 meters per second square. How long will it take to increase the bicycle's velocity from, remember from is the initial, that's where you're starting from, and 2 will be your final. So now we can just plug this nicely into our formula. Let me stretch out a little bit. Okay, final velocity 0.89 meters per second north minus 0.68 meters per second north. We don't have the change in time, so that's our unknown. But the acceleration is 0.53 meters per second square. Now notice that they didn't give us a direction with it, but because it's positive, we can associate the positive direction to be north. So this is north. So this makes our life easier because we could just simplify the top. Which is 0.21 meters per second. And to isolate for the change in time, multiply both sides by the change in time. And then divide both sides by the coefficient of the change in time. So this means that the change in time equals to 0.21 divided by 0.53. Which is really fast, 0.39 seconds. Right? Now, it's not the nicest way to solve this question. Let me just quickly show you an easier one. So from the formula, we have acceleration equals to the change in velocity over the change in time. And since they wanted to find the change in time, we could just isolate it from here. A delta t equals to delta v by multiplying both sides by the change in time. And then we divide both sides by the acceleration, which gives us the change in velocity divided by acceleration, which is what we ended up doing, but it looks a lot nicer because sometimes it's scary to be dealing with numbers at the beginning. Okay, thank you for sticking around still, right? So if you made it this far, it means you really want to learn physics and you're really determined to get a good score. Now, the last question for this video, it's probably very challenging. So if you made it this far, good for you. Question 11, determine the instantaneous velocity at 6 seconds and then determine the average velocity of the motion depicted. So they're asking for two things. The first one is VINS, which is instantaneous velocity at 6 seconds. And then they are asking in part B for the average velocity. Now, let's look at what type of graph they're giving us. We have a position versus time. So in the position versus time graph, to calculate the instantaneous velocity, that's the slope of tangent in the dt graph. And to calculate the average velocity, that's just the slope of secant line in the dt graph. Right, so this is the big difference in this section here. To calculate the instantaneous velocity, which is the velocity at one given moment in time, you calculate the slope of the tangent line. To calculate the average velocity, which looks at a time interval, you calculate the slope of the secant line. So that means that at the 6-second mark, we need to draw the tangent line. So remember, how do we draw a tangent line? We take the point that they're interested and draw the point closest to it and connect them with a line. So this is tangent at t equals to 6 seconds. And then to calculate the slope of the tangent, we use the point that they were interested at, so 6 seconds and approximately 60 meters. And we look for another nice point on the tangent. So here looks pretty good. So at the 4-second mark, the position is 0. So we have our 2 points. So in this case, it's going to be 60 minus 0, 6 minus 4. 60 divided by 2, which is 30 meters per second. Again, your answer might be a bit different than this answer, and that's okay, because whenever you're drawing tangents, it's just approximating, so it's just the best that you can possibly do. As long as you don't have 100 or 0, you're likely to be correct, and also it shouldn't be negative. Now for the average one, they're asking us to calculate the slope of the secant line. So we need to draw the secant line, which is the line that connects 2 points on the graph. So I'm just going to erase this to make it clear. Now, for the secant, you want to draw a line connecting the 2 endpoints. So from the beginning to the end. Because the secant looks at a time interval. So this is the secant line. And this has at the 10-second mark a position of 200 meters. And this is 0, 0. So in this case, the slope is going to be 200 minus 0, 10 minus 0, which is 200 over 10, which is 20 meters per second. So you see the two values are actually not the same. They're going to be different. The instantaneous gives you what happens at one moment in time. The average gives you at a time interval. So this is it for now, and then I'll see you in the next lesson.